Our project mentors were Mike Gilbert and Jason Sortino. We are part of the HPC Cluster Engineering Academy under the direction of Dave Fox.
Hi, my name is Nisha Prabhakar, and I'm a sophomore at UC Berkeley studying electrical engineering and computer science.
And my name is Megan Utter. I am entering my final semester at the University of Maryland, Baltimore County, studying computer science.
So we will discuss the background information and motivation behind our tool, our main development steps, and our final results. We will also go into the challenges we encountered during working on this project and areas that can be further developed.
The Genders tool is an open source LLNL tool that stores information about node configuration. It works by storing a file on every node of the system. There's one file per cluster, and that file is replicated on every node of the cluster. The file stores information about the nodes. For example, the image at the bottom of the screen has examples of some common genders, such as alternate name, and what cluster the file is on, etc.
The command line tool called nodeadder can query the local genders file. Users can ask questions such as, which nodes on this cluster are management nodes? At the top of the slide are example nodeadder queries. The first query is asking which nodes on the local file contain the center attribute. It also specifies that the output should be printed in a host range format. The second command is the same query, except it excludes nodes that have the management attribute, resulting in excluding LGW1.
Lipgender performs the same functionality as nodeadder, except that it's a Python module. When Lipgender, we needed to initialize the genders object with the genders file. The first query is asking what the value of center is for LGW1, and the output is green. The second command checks whether the gender center has the value green anywhere in the file.
There's only one problem with the system. The information that nodeadder yields can only be accessed locally. You have to log into the cluster which you want information about. You would not be able to get more global information, like how many management nodes exist on the entire system. In order to solve this problem, we created a centralized database which stores all the genders information for all the clusters on the system. This database can be accessed anywhere in the system.
The first step we took in our development was deciding between using a relational or non-relational database. We discovered that MongoDB's NoSQL structure was very flexible. There was no need to define a clear structure for the database. However, this could create problems with data consistency. On the other hand, MySQL has a more traditional structure which required rigid relationships between types of data with predefined tables. MongoDB has the edge on MySQL in handling large amounts of data. For these reasons, we decided to use MySQL because of the innate simplicity and rigidity of the gender structure. It makes it easily visualized as a relational schema. There's not an enormous amount of information in the genders files, so the advantage MongoDB has was not really useful for this purpose.
So the image on the right is the diagram we made to plan out the database structure. We have 3 tables. The node table on the top stores the node number and what cluster the node belongs to. This information is concatenated together in the node name field to make a unique primary key. The gender table at the bottom stores the name of the attribute and a categorical description that can be manually entered by a user. The configuration table in the middle connects these tables to store the values of a gender and maps node names to gender names using a join. The config ID follows the same logic as node name, where it is a concatenation of node name and gender name to make a unique primary key.
We configured the installation of the genders library to be specialized towards our application. We inputted settings so that the make command only created Python extensions. Originally, Lipgender was built with Python 2, but we wanted this to run on Python 3 to allow it to have a longer lifecycle since a lot of tools are losing support for Python 2. In order to change the Python modules so that it was built on the newer version of Python, we inspected the configure file and changed the shell variable Python to successfully install genders with Python 3. We then used the newly installed Python module to query the local genders file and feed it into the database. We looked for a few cases. If there was data that was on the local genders file but was not in the database, we inserted it into the database. On the other hand, if there was data that was on the database but not on the local file, we deleted that data. Lastly, we updated any values that had changed.
We then adapted the script to run on a central node with the CF Engine repository. On our test cluster, we created a simulation of the CF Engine directory tree to develop our methodology. The image on the right is a diagram for that simulation. We have an overarching CF Engine directory, and then within it, a clusters directory. Further inside, each cluster has a directory which contains a genders file. We used bash commands to create a file listing the paths to each genders file in the tree. We looped through each of the file paths and pulled the contents at that path into a local temporary file. Finally, we sent that temporary file through the previously made insertion logic.
Lastly, we created Python methods for users to query from the database through the command line. We use the argparse Python module to create command line options. GendersDB querying options mimic nodeadder, except that it gets information from the database. Users can give commands to display all of the nodes that have a specific gender, all the genders that exist, and more. To format some of our output, we utilized a Python wrapper of the command line tool HostList, which was developed by Chris Musa, a former HPC Academy intern. HostList compresses a results list into a more readable and functional output.
Since we wanted our tool to be as easy to install and maintain as possible, we decided the best option would be to structure our code into a Python package. This allows us to keep our scripts modular, so extending this tool to include more features would be simple to do. We learned that we needed to add a setup.py file and additional markdown documentation into our repository.
We dealt with a few different challenges during this project, one of which was the installation of genders. When we first tried installing, we had quite a few errors that we did not know how to deal with. To solve these errors, we investigated the output of running the configure file with the help option to learn about the different configuration options. Since we were only interested in the Python module, we disabled it from building extensions for Java, C++, and Perl. We discovered that there are many dependencies that our node were missing after writing make. So we looked at the errors that the command line outputted and used the yum provides command to find the specific package. As of right now, we need to set some additional shell variables such as Python path and LD library path to allow the package to run smoothly. But in the future, this should be resolved and no longer be necessary.
The most challenging part of updating the database was finding the data that needed to be deleted, especially after the CF Engine simulation tree was introduced. We tried multiple algorithms, but we finally ended up with one that worked. As each genders file was looped through, we compared its contents to what was in the database. Using this comparison, we updated two lists, one which contained information to delete and one which contained information to keep. After all the genders files were iterated through, we were left with a comprehensive list of items to delete. Another challenge we faced was installing MySQL onto our test clusters. In order to do this, we needed to download the repo, prepare the repository, and install and start the MySQL server. We then needed to append the file path of MySQL to the bash profile. Initially, when MySQL is set up, you are given a temporary password to access the server. This wasn't explicitly said in many resources, but once we deduced this, we wrote a bash command to retrieve the password, lowered password restrictions, and then changed the password into one that was more appropriate and easier to remember.
So in our the first step users need to take is to set a password using the command in the image at the top of the slide. We theorize that if an engineer had root access on the central node, there doesn't need to be additional security for this database. So storing the password would make it far more convenient to run other commands. The password option saves the inputted password into a file, which is then read for future options. The load option in the middle of the slide runs the insertion logic we discussed earlier. It updates the database to reflect the contents of the cluster's genders file. The descript command allows users to enter in a short description of what an attribute does. Description is not something that can be recorded on a traditional genders file, so this type of documentation was not possible on earlier tools. So in the example at the bottom of the screen, I added a description to the alt name gender, and we can see that it was reflected in the database.
So here are some of the examples of the many query options that we implemented for this database. -Q is one of the most common ones. So what it does is it returns the result of the passed-in query in host list format. So here it returns which of the nodes in the database has the center attribute. In the middle, the -Q checks if the node name is met by the specified conditions. If the condition is correct, the exit code is set to 0, while if incorrect, it is set to 1. So here we check if the LGW1 node has the center attribute, which it does, so the exit code is set to 0. Lastly, there's an example of -V at the bottom, which prints the value associated with the node name and the gender. So LGW1 center attribute has the value green, which is printed to the screen. One way we could develop this database further is to configure the database to update automatically whenever someone changes a local genders file. We thought that we could use GitLab's continuous integration for this purpose. Also, we would want to diversify the types of access to the database. For example, some users would have view-only access, while others would be able to edit genders descriptions and update the database. Furthermore, a configuration file could be used for more advanced password management. Thank you for listening. Are there any questions?
All right. Don't be shy. If there are any questions, now's your chance.
I had one question. For like the description field, is that going to be mandatory that has to be filled out? It might be a good suggestion to have that be mandatory.
Right now, it's not mandatory. Like there's like a default value that we have, which is just none that you can change. But it would be, we can make it be mandatory without it causing too much trouble.
Okay, a second suggestion might be to record the user. Maybe you already do this. Record the user that created the gender, so that later on somebody can ask more about it and know who to ask.
I'm curious what aspects of this were most challenging for you two.
So like the automatic deletion, we probably spent the most amount of time working on the algorithm. But then like the configuration when we're installing genders with Python 3, I haven't done anything that was like very similar to that until this internship, so that was a challenge.
Yeah, the very first part was definitely a challenge because it was like completely new for me, so it was kind of like floundering before I was figuring out what's going on.
What about the mechanics of just everything being remote? How did you deal with that? Were there any things that we could have maybe done better to make it easier?
I think this was like, I don't know how this could be improved, but like occasionally there was times when my workspace was really like disconnecting every few minutes, which was obviously not the best for trying to code something, but I think that's just like something that's always going to happen if it's remote. But other than that, I think it was a really good experience.
Yeah, I agree. I think we had like a lot of collaboration and we used like a lot of video calls to help with that, and it worked pretty well.
Did you find that you had any, I guess, differences in your background where you ended up like complementing one another, or one of you was ahead on one thing and one was ahead on the other, and you could kind of swap skills?
Yeah, I think Megan had done a lot more database design than I have. So like when we were coming up with the like database diagram, that was pretty like useful because it was easy for me to catch up on that since Megan had like an idea of what was going on there. So that part was really useful. I think in other areas where we were pretty evenly matched.
Awesome. Thanks.
All right.
Okay, ready?
Mhm.
Awesome. Good morning, everyone. My name is Ben Ryan. I'm a senior at William & Mary studying computer science and Japanese.
And I am Christian Palomo. I am a final year student at CSU Monterey Bay studying computer science as well.
And today we'll be presenting on implementing and interfacing with KVM. This is a project we've been working on as part of the High Performance Computing Cluster Engineering Academy at Lawrence Livermore under the mentorship of Dave Fox and Gene Schuler. Next slide, please. So to begin, we should introduce what a virtual machine actually is. A virtual machine, or VM, is an emulated system that runs in conjunction with a host operating system and physical hardware. The hypervisor is the hardware or software layer that separates physical hardware from the operating system to allow for the creation of virtual machines, of which there are two types. A hypervisor is considered bare metal, or type 1, when it runs directly on the hardware, as opposed to a hosted hypervisor, or type 2, which runs on the operating system like any other program or process. Bare metal hypervisors provide more efficient usage of resources than hosted hypervisors. Bare metal-based VMs are therefore more efficient for smaller or specialized tasks, ease of testing configurations prior to deployment of new technology, but both types of hypervisors allow a virtual machine to mitigate the need for new physical hardware in cases where a small task might have required additional hardware to be purchased. For example, if you were deploying a small web server, you wouldn't need to buy a whole new hard drive or a whole new set of processors to handle that. So recently, the use of container interfaces such as Docker have become popular. These programs typically work in a similar way to a hosted hypervisor, a virtual machine, with the most major difference being that while they are more isolated than a standard process, share an operating system and potentially other resources. A virtual machine always has its own operating system. Next slide, please. So now that we know what a virtual machine is on a high level, I'm going to introduce kernel-based virtual machines. So kernel-based virtual machines, or KVM, is a type of virtual machine that uses the Linux kernel as a bare metal hypervisor. This allows the host machine to treat every virtual machine as called a guest, as if it were a Linux process. Therefore, every guest has the same level of access to physical hardware as any other process and can easily and efficiently be used thanks to tools that Linux already has built in, such as the task scheduler. The main benefits of KVM specifically is that it is built into Linux and is extremely efficient considering that the Linux kernel acts as the hypervisor. This means that it has an inherently unrestricted access to the physical hardware and Linux tools available. This in turn provides features for enhanced security, scaling, and uninterrupted host migration.
Some of the high-level goals that we set going into this project were to set up nodes in the student environment cluster to run KVM, develop a process to build and deploy various operating systems, preferably with automation, and finally to translate these tools and processes into real-world applications. Although KVM comes built into Linux, there is a bit of setup required on the host machine before creating VM guests. The first thing to do was to make sure that the CPU of the host machine where you want to create the guest supports hardware virtualization, which can be done by using some simple commands. The next step after this was to enable virtualization in the BIOS of the host machine, which can be done by rebooting the node and accessing the BIOS when prompted during the boot. Inside the BIOS, some options will need to be set to enable virtualization technology, and once the machine is booted up, virtualization will be enabled on the node, and the next step is to install the required packages. After the packages are in place, there are a few more steps to make sure the node is set up properly. We need to enable libvirt on startup and check to see if the KVM module has loaded properly. Once that's confirmed, the last thing to do is allocate new IP addresses and names for the guest VMs that are going to be created. And this is done by editing the etc host file in the management node of the cluster, and then doing the same thing in the host file of the node that will be hosting the guests. After these tasks are complete, the node is set up to create guest machines. Before creating a guest, an ISO file is needed for the operating system. Download your desired ISO from a mirror and make sure that it is placed in the correct directory. This will be used in the Vert install command, which is the command line tool that's used to create a guest. Within this command, you're able to specify flags to define the specifications of the guest machine. Some of these options that you will need to set are the name of the guest, number of CPUs, amount of memory, OS variant, and location, which will be the path to the ISO image that was downloaded. There's also an extra arguments flag where we can specify things such as which console to use and pre-configuration files to use during installation. And upon execution of the install command, the guest VM will be allocated and installation will begin. The user will be prompted to enter some base configurations toward the end of the installation, most of which can be left as default. And after that's done, system will boot up. Implementation of guests with a Debian-based operating system is mostly very similar to the process we just laid out for Red Hat systems. You will still need to use the Vert install command, but in a bit of a different way. We figured out that a Debian ISO image functions a little bit different, and it cannot be booted using the location flag as we did before. So instead, Debian systems use a CD-ROM flag in the install command. The problem with using this is that it will not allow for extra arguments, which becomes a problem when trying to use pre-configuration files. And the way around this is to still use the location flag, but instead of giving it the path to an ISO image, we just give it the URL address of a network boot mirror. Another difference in implementing Debian-based systems is that the serial console is not automatically configured during the installation the way it is with something such as CentOS. So the way to work around this is to SSH into the guest system once it's up and running and edit the grub file. In some cases, we experience trouble with connecting to the guest via SSH, so the other option to fix this issue is to remove the no graphics flag from the install command and then use Vert Manager along with VNC to access a GUI of the VM where we can configure these changes in the grub.
So most virtual machines would simply not be useful if they could not communicate with other local machines or the wider internet. So as we've discussed, virtual machines are emulations of hardware, and therefore any network interface that a guest might possess are virtual themselves. So to connect a virtual network to a physical network, a bridge device must be set up to allow communication between the two. For example, if you were to set up a basic guest machine using the methods we have described, in order to interface on the physical network the cluster itself utilizes, you would have to define a new network bridge. The clusters that the Academy has configured throughout their program have a back-end Ethernet network as well as an InfiniBand network. The Ethernet network is managed by a physical switch, and the nodes use the EM1 interface to access that switch. If we create a virtual bridge device that assigns and passes IP addresses via DHCP, then instruct EM1 to look for that bridge device, we have essentially created that bridge between the physical and virtual networks. To visualize this, it would be as though the port that a given node physically occupies on the Ethernet switch now acts as a virtual switch itself, assigning multiple virtual ports to one physical port that the virtual machines can occupy. The virtual bridge device BR1 then bridges the physical network via EM1 to the virtual network that the VMs share. Next slide, please. Now, as you might imagine, installing different distributions of Linux or any other operating system on a guest is a time-consuming and error-prone process. Furthermore, certain scenarios might need even more robust control over the operating system that is installed, such as kernel version. Without automation of the installation processes, use of the virtual machines for testing over various hardware and software configurations would simply not be practical. While one could install a guest via a GUI tool, using the libvirt package and Vert install command opens the possibility of automation through bash scripting and Ansible. Creating a script that can run the command that defines and creates a virtual machine, especially if if that script has capabilities to accept user input, means that a lengthy command need not be typed repeatedly. However, one would still have to proceed manually through the installation prompts of the operating system. Many Linux distributions provide a way to automate the actual installation through pre-configuration files. This pre-configuration file can be injected into an operating system's ISO image or via network boot file with a simple addition to the vert install command. These files provide instructions on operating system configurations, packages to be installed, users to be defined, just to name a few options, and those allow the installer to run without any user intervention at all. Therefore, the resulting guest will be fully configured from the original vert install command, completely automated. Some common forms of pre-configuration files are Kickstart for CentOS / Red Hat-based distributions, Preseed for Ubuntu or Debian distributions, and AutoYaxt for OpenSUSE and SLUS distributions.
Some other tools that we used, the Versh tool allows for some basic commands such as displaying a list of currently active guests on the machine, connecting to a guest, and destroying a guest instance. And also, as mentioned earlier, another tool that we used was Vert Manager. Vert Manager is the GUI tool that's used to manage virtual machines as opposed to libvirt for using command line. In certain cases, we were not able to set up a serial console for a guest by connecting through SSH, so we were able to use Vert Manager along with VNC to get a virtual desktop of the guest we created. In order to get a real VNC to work together with Vert Manager, there is some additional setup required. And another tool that's worth mentioning is Overt, which is an open source virtualization management platform that was created by Red Hat. Overt is useful for large-scale kernel-based virtualization management. As far as what we accomplished, Ben and I were able to outline the procedures to create guest instances of various Linux distributions. It was our first time working with virtual machines and KVM in general, so there was a lot of research involved at the beginning of the process, followed by a lot of trial and error as we figured out how to integrate KVM. We made sure that we created detailed documentation of the procedures we used and things that we learned in this process. And it was also important that our documentation can be used for future reference by other admins, since this could potentially be implemented to enhance CI workflow. These operating systems that we worked with include CentOS 7 and 8, Debian 9, Ubuntu 18.04 and 20.04, and OpenSUSE 15.2. We made sure that these systems were implemented with base configurations to install required packages, create a test user with privileges, and run an automated install of the operating system. Later on, these guests can serve as systems to build test environments on. So for future plans, Ben and I, we've learned a lot about working with KVM during our time here at LLNL, but our time as students was a bit limited. For our future plans, we had a couple of goals that we would have liked to work towards if time had allowed. And the first would be to set up and configure a guest running TOS as the operating system. While we did not get a chance to try implementing this, it would likely be pretty straightforward considering TOS is a Red Hat-based operating system similar to CentOS, which we worked with and know how to implement. And then another goal of ours was to apply KVM in order to create test environments for MSR-safe kernel modules. A variety of Linux distributions for these environments is important because it would allow for testing of modules on various kernels. These test environments would then be used to respond to continuous integration requests in GitLab by using a scripted tool to run the requests on the allocated image, capturing results, and then deallocating and cleaning up the instance.
Okay, we want to thank you so much for your time and attention. And at this point, we'd be happy to answer any questions or take any comments that you might have.
So this is Jean. How did you guys find working remotely as a process? Was it an easy thing to do, or I think, Ben, you were in Chicago and Christian was here in Livermore or Pleasanton.
That's right. I'm in Livermore. It did take a little bit getting used to, and it definitely wasn't ideal, but we were pretty much able to work well together, and it didn't hold us back too much at all.
Yeah, adding on to that, like Gene said, I've been working from just outside Chicago, and yeah, of course, it would have been preferable to be at the lab in person, and beyond expected, technical hurdles such as working with the Amazon desktop and things like that. I was very happy with the experience. I didn't really expect to be able to get an impression of the lab and its culture just from working remotely. I thought I wouldn't be able to have that opportunity, and I was really impressed. I was able to get that impression, and I really thought that was a testament to how well the program was run and how much support that both our peers and the staff at Livermore and LC were willing to give.
Right. Yeah, because you were a 2-hour time difference and Megan was a 3-hour time difference.
Yeah, that was a little inconvenient, but it's totally manageable.
So what was the hardest thing you guys had to deal with in working on your project this summer?
Well, so Christian may or may not agree. Honestly, just working with the pre-configuration files could get really tricky because they each do everything a little bit differently. And while libvirt provides the command line interface to create guests, as Christian described with the Debian issue with the CD-ROM flag and location flag, they got really picky, and finding consistent documentation for each distribution could be really difficult. So you'd find yourself, trying to create a guest, and once you did that, you try and automate it, but you just get all sorts of weird errors and inconsistencies, and just kind of working through that, trying to find documentation that was relevant to that was definitely the most time-consuming and challenging part for me.
Yeah, I would definitely agree with that. That's what I was going to say as well.
Okay. That's a great project, though. I loved hearing about that. I learned some stuff. Thank you.
Thank you.
That's great.
So yeah, thanks for doing that, guys. Any last questions before we go to the third team?
Okay, so our project is Foundations for Architectural Level Application Optimization. Our mentor was Barry Roundtree, and we were part of the HPC Cluster Academy as well.
Hi, my name's Sunshine Belingit, and I'm an undergraduate student at California State University East Bay, majoring in computer science.
I'm Martin. I'm also a student at East Bay. I'm going to graduate this semester.
Hi, I'm Valen Yamamoto, and I'm a student at UC Irvine.
So our research question was, when can we say architecturally speaking that an algorithm cannot be improved further on a particular architecture? So what we were trying to do is see how far we could push our server, what we were using. And the reason why we want to do that is because we wanted to explore MSRs in an HPC environment, and we wanted to explore optimizing code for that environment, specifically to help optimize how HPC runs their supercomputers with that the software they're using. So what we needed to do is provide a roofline analysis and things like utilization measurements. We also we started with algorithms such as a naive matrix multiplication, and then we used Stratton to kind of judge the differences. And then we had our own type of algorithm with Jacobi, which was like a matrix convolution type of project. Anyway, our environment was Hyperion. So our foundations were we knew a little bit of C, and we got to learn more about p-threads, analyzing assembly output, which we had some knowledge of but weren't experts in, and implementing existing algorithms. We got to use R to generate test and answer matrices, and then we got a little bit more experience with GDB, which a lot of us didn't even have any. We use bitwise manipulation and number representation to actually look for these MSRs, which are model-specific registers. And so they give us those registers in hexadecimal numbers, and then we have to turn bits on and off to manipulate those registers. So, as I said before, MSRs are model-specific registers, and they control various things, and we use those instructions for debugging, program execution tracing, and performance counter monitoring. And those features were good. Down below, you'll see that we have a picture of an MSR, and what that's describing is the different options that we have. And the way that you access those options is depending on how what bits you turn on and off. So that's why we needed a bitwise operation, so that we could actually control those counters and have them do what we wanted them to do, so that we could look for bottlenecks and other types of things when we were running our code. So another thing that we used was MSR Safe. That module was helping us to work with these MSRs. When we were using the batch interface, we use it for reading and writing to the MSRs, and it worked pretty well. So with the MSR module, MSR Safe module, they had struct, two structs. One was a batch ops, and another one was a batch array. And so if you look at the two pictures below, you'll see that there's different parameters that are needed, and it kind of describes what they're used for. So the first one was what CPU you're going to execute it on, and the second one is, are we going to write to it, or are we not? Are we just going to read to it? The third one would be checking for errors. The fourth one, where it says MSR, is just what's the hex value for that MSR. Then MSR data is either what our results were or what we inputted for that MSR, such as like changing options. And then the write mask was what we applied to the MSR for writing. On the other side, you'll see that the MSR batch array, that actually was the number of operations we used for that struct, and such as how many times we use the counter, right? And so we put that in array, and we specified how many cores we had and how we were using it. So the MSRs that we used were imperf and aperf. Imperf is increments at a reference cycle frequency, and then aperf is the number of cores cycles while the logical processor is not in the hole. So they kind of helped us understand the frequency and the clock cycles. Below, you'll see that this is how we use, this is the math that we use to actually find average frequency and time. To make sure that the time was correct, we actually used get time of day to kind of see if we were in the ballpark, so that we could actually say that the time that the MSRs were reporting were correct. So just to make sure that our math was right. And then, so we had other performance counters that helped us with cache access and misses, as I mentioned before, clock cycles and instructions that executed. Below, you'll see that we have that same MSR again, and it's just a diagram of what it looks like. And then to the right of it, you'll see that there's a list of different ways that we actually access those options in those MSRs. So
again, the MSRs provided us the ability to measure performance. Here you can see a snippet of those values. By reading MSRs, we were able to get values for APERF and MPERF, LLC reference and misses, which are the cache access and misses, instructions retired, which is about the number of assembly instructions executed, and memory loads. With that data obtained, we were able to calculate average frequency, elapsed time, instructions retired per cycle, last level cache misses per instructions, and memory loads per cycle. Next slide, please. So in our project, we implemented Jacobi as mentioned earlier. In Jacobi, you have a matrix of size n times n, and each value represents an initial temperature. For each index, excluding two constants for the heat source and heat sink, the temperature at time t+1 is the average of the temperatures of the surrounding locations and itself. So picture a tic-tac-toe board, and in the center element, you would find the average of all of the 9 sections. This matrix calculation would continue to iterate until the difference between t and t+1 is below a selected threshold. With Jacobi, we introduced MSR measurements and roofline analysis concepts. Here you can see that what happens when divvying up Jacobi between threads. When you use only one thread, the time it took to complete the program was the longest. But as we used more threads, the timing didn't continue to decrease across the board, but actually plateaued at around 11 threads. Next slide, please. Another algorithm we used to compare was a naive matrix multiplication algorithm. Essentially, what's happening is that an index resulting value in a result matrix is finding the sum of multiplying a row with the first matrix and a column with the second matrix. Next slide, please. So the methodology for matrix multiplication was to ensure we were reading the time immediately before and after the matrix multiplication calculation. To get the values of the first and second matrix to multiply, we read values from other files that had random values. We then used R's matrix multiplication algorithm and stored the results in a new matrix. To note, we also had the opportunity to divvy up the calculation between threads and compare with other iterations. With these comparisons, we used Python with matplotlib to generate graphs. Next slide, please. On the left, this graph shows the instructions per cycle versus the matrix size. What ended up happening was that even though we increased the matrix size, the instruction count increased, but the APERF increased faster. Therefore, we could determine that as the matrix size approaches infinity, the instructions per cycle decreases. On the right, this graph shows cache misses per instruction versus the matrix size. We noticed that when we increased the matrix size, the cache misses and instruction count also increased. Therefore, we concluded that as the matrix size approaches infinity, the cache misses per instruction also increases. With these two conclusions, we determined that as the matrix size approaches infinity, a naive matrix multiplication becomes increasingly more memory bound. Next slide, please.
And because we determined that the matrix multiply was memory bound, we decided that we should probably do something to bring down the number of memory loads, or at least make it faster to read these values from memory. And in order to do that, we would read 6 numbers in advance and save them in the cache so that it would be faster to access them. And as you can see, in the blue is the original, and in the orange is when we were reading those values in advance. And you can see that on the left, the time is dramatically faster than it was without reading those values, and that on the right, the instructions per cycle doesn't drop like it did when we weren't reading those 6 values. Next slide, please. And to further optimize these algorithms, we looked into the Intel Intrinsics library, which gives us access to assembly-coded functions, which are Intel's version of SSC instructions. And these essentially provide vector functions for packed doubles. And so, for example, vector addition, vector subtraction, and especially in our case with the naive matrix multiply, a dot product. And then we would compile the code with the MR equals native flag to make sure that the compiler was optimizing for our correct local architecture. Next slide, please. And so when we were looking at the intrinsics, One thing we also looked at is how many values in advance could we read to get the best result. And if we see in the smaller graph, as we increase that number larger and larger and larger, all the way up to 128, time actually got worse and worse and worse. And in the larger blow up of the smaller section, we can see that the best time was actually when we read 8 in advance. And that does seem a little bit strange because we assumed that we could read more values into cache without it overflowing. So that's something we may look into if we have more time. Next slide, please. We also looked at the Strassen matrix multiply algorithm, which is a recursive matrix multiply algorithm that trades less multiplications for more addition and subtraction. The time complexity is a little bit lower. It's about n to the 2.8. However, this does hide a very large constant in front of n, which is why, next slide, please. You can see that the Strassen matrix multiply, which is in the orange, actually isn't faster than the naive matrix multiply until the matrices get large. In this case, about 8,000, which is why we should optimize this. That this may be more of an option on smaller matrices as well as larger matrices. Next slide, please. And so in order to do this, we optimize the more serial portion of the function, which includes the making of the temporary matrices and the base case. So we pulled the base case out to n equals 2 in order to use Intel intrinsic functions there. And then we would make the the intermediate matrix addition and subtraction with the Intel intrinsics. As you can see, much like the naive matrix multiply, that the one with Intel intrinsics, which is again in orange, is dramatically faster than it was originally. Next slide, please. So over the course of the internship, this is kind of our final data on how our matrix multiply optimization has gone. As you can see, the original, which are denoted by the X's, are dramatically higher than what we have optimized them to with Intel intrinsics, which are the solid dots. So hopefully, with the time cut almost more than half than what originally was, people can perform more matrix multiplication with in less time. Next slide, please.
So the takeaways and what we think is next. We learned a lot about pointers and threads and makefiles that we didn't know before. We learned about MSRs, Intel forensics, and root-line analysis for algorithms, which was something that we didn't know too much about when we came into this. We learned more about bash scripting, Git and tmux and Vimtrix, which Vimtrix was something that we actually took a lot of advantage for. We had trouble setting up our environment and coordinating between kernel calls and writing into the kernel. What would happen is we would have something written into the kernel, and then another program would come back and say that's not right and change it. And we didn't know if we were the one doing that or if it was another program editing it for us. So what's next for us is can we always try to optimize more? Can we make it more efficient? And then school's going to start, so we need to take a nap. And these are sources that we used. Is there any questions?
So yeah, this was very impressive. In fact, all the projects were very impressive. I was just going to note, I mean, performance analysis like this is a real niche kind of skill. I mean, it's a great thing that you got to work on. I'm wondering, were you able to leverage what you've learned in school going into this? I know you said you learned a lot, but was this just totally, new territory for you? And does it make you interested in pursuing this type of aspect of computer science?
So it wasn't new for me. I'm sure it wasn't new for some of the other people that were here, but it wasn't like we had an in-depth knowledge of any of these things. MSRs were new for me, but working with assembly language and then having computer architecture definitely helped. But I felt like that it was like another beast trying to understand what was actually happening with these performance counters and understanding the Intel documentation, because there is some parts that are lacking in explanation, but the documentation as overall is actually pretty well documented.
Yeah, for me, I think it was a little bit different because the other two, I think, have taken a lot more classes than I have. So Barry would say things like, I need you to write this code in C, and then I need you to compile it into assembly, and then I need you to count the instructions. I would be like, okay, well, how do I compile C code, and then what is assembly, and how do I count it? So a little bit of that was like, I was like spending a lot of time on Google and like trying to figure out what was going on, like in addition to just what is an MSR, like what is an Intel intrinsic instruction. So, I mean, I think I learned a lot, and I think it's really cool, and I think that I probably will spend a lot more time looking into stuff like this in the future.
Great. Good.
Yeah, I would have to say that's almost the same for me. Like I've heard a lot of these terms, and but ever since I started the computer science, I've always been thinking about what optimization can there be and what are the bottlenecks. So yeah, I've heard some of these terms and whatnot throughout school, but we never really got to dive deep into it like we did during the internship.
Great.
So I got a quick question. You know, the tool is called MSR Safe, and so was it safe, or did you find cases where you actually could mess up the kernel? Did you ever crash the nodes or anything like that?
No, actually, we didn't. It was actually pretty safe on our end because most of the time we were just writing to performance counters, so there wasn't really anything that would break the kernel in any way. There was one time where we were trying to cap the clock frequency, and that was the case where other kernels were coming in and writing over it as soon as we wrote our program. So in that case, we may have broken something, but something was like going behind us and fixing it for us, so nothing broke. But I think it did its job very well.
Good.
So what was it like programming in R?
Oh, it wasn't a whole lot of code. It was maybe like 5 lines. Just create one matrix of random normalized numbers, create a second matrix of random normalized numbers, multiply them together, create a third, write them all to a file. I've done a little bit in school, so this is kind of cool to see it being used in a situation where it's not just, a replacement for integrating the normal distribution. So I think just knowing that there are other tools out there, and I think having that other matrix multiplication to check ours is very helpful.
Okay. Any last questions for the whole group or for this team?